Next up is Alan Cudmore from NASA Goddard Space Flight Center. He's going to be talking to us about platform updates for the Caelum 7.0 release of the core flight system. Alan.
Okay, thanks. So I guess I win the prize for longest title so far, right?
I think so.
So my name is Alan Cudmore. I work at NASA Goddard Space Flight Center. And I'm happy to be here to talk to you today about the latest platform layer updates for the core flight system software. Next slide, please. So for this presentation, I'd like to give you a brief overview of the core flight system platform layer, which includes the operating system abstraction layer, or OSAL, and the platform support package, or PSP. Following the introduction, I hope to give you some insight as to how the CFS system starts up, how it handles exceptions, and an overview of some important, CMAKE files. And finally, I'd like to provide a few porting tips if we have time. So obviously, there's much more to the CFS platform layer than I can present in 20 minutes. So I hope to give you a gentle introduction to the OSAL and PSP while highlighting the significant changes since the original version of the code. Next slide, please. So let's start with an introduction to the platform layer. The core flight system, or CFS, provides a layered architecture as illustrated on the right, with the platform layer highlighted in blue. So the platform layer consists of the operating system abstraction layer, or OSAL, and the platform support package, or PSP. The OSAL provides a portable application programming interface, or API, to the underlying operating system services. The PSP provides the glue logic and startup code necessary to make the CFS work on a specific combination of an operating system and processor card. So what do I mean by this specific combination? A couple of examples include a Raspberry Pi running Linux or the POSIX OSAL, or a RAD 750 running VxWorks. So together, the OSAL and PSP allow the CFS to run without modifications on multiple targets, and it makes it easier to port the CFS to new targets. At Goddard, this enables us to run the exact same CFS code on our biggest flagship missions all the way down to our smallest CubeSats. Next slide, please. Okay, so let's get into a little more of the details about the OS abstraction layer, or OSAL. The OSAL provides a portable operating system API for real-time and general-purpose operating system features. The OSAL abstracts services such as tasks, queues, semaphores, mutexes, files, timers, and network sockets. Pretty much everything we need or could possibly need to run something like CFS. The upcoming release of the OSAL for the CFS Caelum release supports running on Linux, both 32 and 64-bit variants, RTEMS for version 4.11 and 5.1, and VxWorks versions 6.9 and 7. In addition to the OS API, those primitive operating system APIs I was describing, the OSAL provides startup code for abstracted applications. This is known as the OSAL Board Support Package, or BSP. So what exactly does that BSP provide? Each operating system has a different way of starting up applications. For POSIX, the entry point is main, while RTEMS has init for its application entry point. So the OSAL Board Support Package provides a common entry point and structured startup code for OSAL-based applications. So the OSAL BSPs that we currently have in there include generic Linux, generic VxWorks, and something we call PC RTEMS, which supports our RTEMS test platform. This is actually very close to being generic RTEMS as well, and that's really the ultimate goal. Next slide, please. So continuing with the OSAL, I wanted to highlight one of the big changes from the legacy OSAL code. Starting with OSAL version 5, which was included with our CFS Aquila release. I think I said that right. The OSAL provides a layered architecture. Previously, each OSAL port provided a separate implementation for each OS, meaning there was no real shared or layered code. This means that the VxWorks implementation may have not handled each error condition or handled all the parameters the same way as, say, the RTEMS or Linux versions did. So there are several advantages to this layered architecture, including minimizing duplicated code, assuring that a consistent implementation is done for each port, for example, all the error code checks, locks, and so on, and making it easier to port the OSAL to a new OS. And this is kind of reflected in the code size. For example, in an older version of the OSAL 421A, the RTEMS implementation required about 5,600 lines of code. With this new layered architecture in some of the shared modules I'll describe in a little bit, that implementation for RTEMS is down to about 3,200 lines of code. And this is also for a more robust, consistent implementation. So taking a quick look at how this code is organized, when you take a look at the repository, we have several key directories. We have the top level shared API source files. These are located in source OS shared. This is where the actual APIs are defined in the code, and each application that uses the OSAL will call these functions. And I'll show an illustration of this soon. Then we have our operating system specific low-level implementation files, which currently include POSIX, RTEMS, and VxWorks. Finally, we have a portable low-level implementation for all the files that can be used across more than one OS. This helps to reduce code duplications where operating systems share a particular API, thinking like network sockets or file systems. Often this code can be shared across several implementations. So this directory with shared implementations also contains stub implementation files. So you can exclude features that a target might not support, like for example, network. So let's take a quick look at a couple of simple startup examples. Next slide, please. I didn't mean startup, I meant API examples. I'll get to the startup next. So in this first example, we have a shared high-level OS API at the top called OS task create that creates a thread or a task in the system. This function contains all of the code that's common to all of the ports, and it would otherwise be subject to cut and paste implementations and maintenance and errors. So you can see that this OS task create function eventually calls OS task create impl, or the implementation. So that's the OS specific implementation for that API. In this example, the implementation module is for the POSIX port. The advantage here is that the OS task create impl function only contains what's needed for the POSIX port with no unnecessary code duplication. Next slide, please. So this is a second example of the OSAL layered architecture, and it highlights the use of portable implementation modules. In this case, we have the OS socket open call at the top, which again is in the shared high-level API. The difference in this example is in the implementation. We currently have two different implementation files for this API. One is for the standard BSD sockets on the left, which they're portable to a number of different operating systems, like actually all three at the moment. And then on the right, we have the no-op implementation, or kind of the no sockets implementation. So these files are selected by the CMAKE list file for that particular OS port. So for example, if we don't have network support on our target, we can just select the no sockets implementation file for our port. Or if we have BSD sockets, we can select the BSD sockets implementation. And note that if we had a third option, like if we had an OS that used the lightweight IP stack, instead of BSD sockets, we could provide an implementation for that, whether it was portable or actually target specific. So really you just provide the module you need and you select it in the CMAKE file. Next slide, please. So let me go over a few details of the OSAL board support package, as there is an important difference in how this code is used compared to earlier versions. So previously, the OSAL BSP directory contained startup code, build rules, and toolchain options for a specific target. This BSP code was used for examples and standalone OSAL applications. In other words, OSAL without the CFS. So the CFS didn't use this code at all, but instead it used the platform support package provided startup code, build rules, and toolchain options. And this caused some level of confusion and of course code duplication. It was sort of confusing. It's like, is my code starting up in the CFS PSP, or is it starting up in the OSAL BSP? So starting with OSAL 5.1, the OSAL BSP provides a common entry point, and the PSP now leverages this startup code rather than replacing it. So this brings consistency to the startup code and facilitates unit tests as well. I'll show an example of how this startup works right after I introduce the PSP. So currently the OSAL BSP code includes the OS-specific startup code, shared BSP files, which again help duplicating code, and finally build rules and definitions. So note that the cross-compiler specific commands and options are in the CMAKE toolchain files, and they're not embedded or buried down in the OSAL and PSP directories. Again, this makes porting easier because you don't really need variants of a certain BSP or PSP. So for example, you don't need a PowerPC RTEMS BSP versus an ARM RTEMS BSP, where the only difference is the build commands or the compiler commands and options. Those can all be in the toolchain file. Okay, next slide, please. Okay. So now I'm going to talk about the other major component of the platform layer. We just discussed the OSAL. The second major component is the platform support package, or PSP. So the PSP provides the necessary functions needed to adapt the CFS to a particular operating system and hardware platform combination. So this is functionality that is necessary to support the CFS on a specific hardware board, but it does not necessarily belong in a generic OS abstraction. Like we can't change like the RTEMS OSAL port just to add support for a particular board's watchdog timer, for example. So I mentioned a couple of examples earlier of this combination, like POSIX on a Raspberry Pi or VxWorks on a Rad 750, or if I want to cover two sponsors with one example, RTEMS on a Leon 3 FT processor. And that happens to be one of the projects I'm currently working on. So the PSP provides the following features through startup code and function libraries. So it handles the startup of the CFS. It provides a watchdog API to abstract the watchdog timer to the higher level CFS code. It provides a restart API, basically a way to restart the target board from the higher level CFS code. Provides exception support, which I'll talk about in a bit, provides hardware timer support, file system mapping, and it provides the memory for CFS critical data stores, tables, and of course our CFS volatile or RAM disk. So the PSP also is incorporating the idea of the shared implementation files where we can take advantage of common software where needed. So this is a big takeaway. The trend here is to have less duplicate code in both the OSAL and the PSP, sharing code where necessary, and minimizing the code you need to make new ports. So next slide, please. So this is a list of our currently supported platform support packages. The list includes PC Linux. So this is our generic Linux platform implementation. It's primarily used for CFS test and development, although it is being used on real flight projects, including a bunch of CubeSats at Goddard. So here, the PC name is a little misleading because it is compatible with both 32 and 64-bit Linux platforms, including virtual machines. You know, we've run it on Windows Subsystem for Linux version 2, and a whole host of single board computers such as the Raspberry Pi. In fact, I've run this PSP on something as small as this little $7 embedded Linux board that's about the size of an SD card. I'm not sure if the camera can focus in on this or not, but it's a tiny little board and it has its own embedded memory, and it just costs like $7 US. If you want more details, you can always talk to me on Slack. So anyway, the PC Linux PSP supports multiple architectures like ARM, x86, PowerPC, Microblaze, and MIPS. So really, it's no magic that we're doing here. Linux really provides the ultimate abstraction for all of this. So the next PSP we support is the MCP750 VxWorks. So in the embedded systems world, this might as well be called the Commodore 64 because you really can only find them on eBay. So this is a very specific board for an internal CFS test platform that we have at Goddard. It consists of an MCP750 PowerPC processor card and VxWorks 6.9. It can, however, be adapted to different VxWorks targets, and we do that all the time in our work. So finally, we have the PC RTEMS PSP, or Platform Support Package. So there's that PC name again. This is an RTEMS test platform that targets the x86 PC port of RTEMS, and it's primarily used on QEMU or QEMU to test our RTEMS CFS port. It can also easily be adapted to other RTEMS target boards, such as the Leon family of processors, ARM, and so on. So next slide, please. So now I'm going to switch gears and talk about how the CFS starts through the platform layer. I mentioned that the CFS startup now depends on the OSAL BSP code, so let's take a look at how that works. Next slide, please. In this slide, I wanted to give you a quick walkthrough of how a standalone OSAL example starts up. A standalone application is like an OSAL test or the included tasking example where there's no CFS involved. So let's walk through the steps real quick. So step 1 on the right there is the OSAL entry point, which on POSIX is main. This is in the OSAL BSP for the generic Linux. So step 2 is the OSAL application entry point. It's called OS application startup. This is where the example code actually starts, and that's in the generic code on the file on the bottom. So step 3 in this example, step 3 creates all of its sample tasks for this tasking example using the OSAL APIs. And then when it's finished, it returns to the BSP startup code. In other words, the application startup returns. So finally, in step 4, that OSAL BSP start, it calls OS application run, which is generally used for idle loop and event handling. So as you can see, the code at the top of the screen is OS specific, and the code at the bottom of the screen is portable, and that would run on all the supported OSs that we have. So next slide, please. So now let's revisit the same startup procedure, but applied to the CFS startup rather than just an OSAL example. So as you see here, the OSAL entry point at the top is still the same. That code didn't change at all. But now as we go from step 1 to step 2, we're not calling an OSAL example. We're calling into the CFS platform support package startup code, which contains a replacement for the OS application startup. In this example, the CFE ES main function ends up being called from OS application startup, among other things. There's a lot of other things that are going on here. But this is where the CFS creates all of its resources, starts all of its tasks and everything. But eventually it will return. And when it returns, the control flow goes back to the BSP start code at the top, where OS application run is called, just like our previous example. So again, OS application run is provided by the PSP here. So you can see how these two kind of interact, and they each have their own specific functions without really being duplicated code. So next slide, please. So moving right along here, I want to try to provide a very quick overview of how exception processing happens in the platform layer. And there's a couple of differences here. Much like the code in the PSP and OSAL, the exception handling has been improved. Previously, the PSP would catch an exception and call a CFE executive services function to log that exception and handle the restart. This could cause problems when the PSP called an ES function or executive services function from an interrupt context. In fact, it wouldn't work at all because the ES would kind of would call a lock, which wouldn't work in an interrupt context. So this is the case for some of the operating systems that we supported. And it also violates the layering guidelines by not having the PSP directly call the ES functions, other than some configured callbacks for things like the CFE entry point. So now that the exception handling is completely managed in the PSP, and the CFE executive services will call into the PSP to check for exceptions. So here's a little bit about how that works. So as part of its background task, executive services will poll the PSP to see if any exception events occurred. When an exception does occur, the PSP will immediately notify the ES background task, or it signals the ES background task. ES will call into the PSP when it gets that notification, and it'll collect the exception information and context. ES will then decide through the mission logic what it wants to do, and it'll call back into the PSP to take the appropriate action if necessary, such as a reset, and what type of reset. So next slide, please. So another big change from the early versions of the OSAL and PSP is the use of the CMAKE as a build system. So the following table is a list of important CMAKE files in the platform layer. In the interest of time and not putting everyone completely to sleep, I'm not going to go through these. So I'm just going to point out that a lot of the important files here in this for the CMAKE are actually not buried down in the OSAL and PSP directories. Like in the CFS, these are in our mission defines directory. So unless you create or customize a new OSAL port or PSP, you shouldn't have to go digging all the way down into the directory structures for the CMAKE files that you need to configure. They should all be at a higher level where you can really set things up for your mission. So next slide, please. So last is a few quick porting tips. I know this is a rather simplistic, high-level chart showing the approach you would take for a new port. So let's say that, for example, Joe Sherrill announces that he stayed up all night for a couple of days during this flight software workshop, and he's ported RTEMS to the Raspberry Pi 4. So now I want to make that run. I want to make the CFS run on that port. So given this flow chart, I would first ask, well, do I have an OSAL port already? Yes, in this case, the OSAL supports RTEMS 5.1, and I'm assuming it's compatible with the current head of RTEMS 6. So next, I'm going to ask, well, does it have a PSP port? Well, since I have the RTEMS PSP for the x86 QEMU system, I'm going to need to create a new PSP, but I certainly can use the existing PSP as a starting point. It probably has 90% of what I need. But let's say, for example, I want to port the CFS to, let's say, the Zephyr RTOS on a new SoC system I haven't used before. I'm going to need to go completely down the right side of this chart, saying I need both an OSAL port and I'm going to need a PSP port. So next slide, please. So just a few more porting tips. So first, port the OSAL if necessary, since the PSP port depends on the OSAL port. Then you tackle the PSP port next, and you usually want to start with something that's fairly close. So for example, say 90% of, oh no, I guess what I was going to say is that when you're selecting a PSP to copy for a new implementation, you want to stick with something that's similar to your OS. For example, if my target is an RTOS, like some kind of RTEMS or VX workspace system, I probably want to choose one of those existing PSPs. If it's something like POSIX, like say we're porting to QNX or Linux or something, then I probably want to stick with the POSIX one or the PC Linux PSP. And another thing to note here is that about 90% of the effort in the PSP is probably in 10% of the code. By that, I mean that you can make a lot of progress getting started and getting the CFS and a lot of the apps up and running before you really have a completed PSP. You really just need to get things kicked off. At Goddard, we usually get the CFS in our apps up and running with a minimal PSP, and then we go back and fill out the functionality in the second release. And finally, remember that the cross-compilation toolchain defines are always in the CFS mission definitions. They're not really buried down as part of that implementation. Okay, next slide, please.
Alan, you're just about out of time.
Okay, all righty, thanks. So I guess I'll just leave this here. We have pointers to our GitHub repositories where everything is open source. And I would suggest if you wanted to get started, you can use the CFS bundle. And next up is our Caelum certification and release. And eventually we hope to get to the SMP integration for the OSAL. So anyway, since I used up all the time, I'll be happy to jump on the Slack channel and handle any questions there.
All right, excellent. That was fantastic, Alan. I really it broke my heart cutting you off.
Oh no, that's fine.
So we have several questions in the Q&A, and I have several of my own. And I wanted to offer, if you think there are any side Slack channel or dedicated Slack channels for any of this stuff that you're talking about, I honestly think that, I mean, if it doesn't fit in specifically under CFS, because that would work too. We're happy to accommodate that because I think this is going to generate a lot of conversation. So,
yeah, any's fine with me. I'll be on the Slack.
Okay, so we'll probably go ahead and copy this over to the CFS Slack channel, and so we actually have a few minute break before our keynote coming up next. So thank you so much, Alan. That was really I really liked that presentation.
Okay, thank you. And the one thing I failed to mention due to time is I would like to acknowledge Joe Hickey and the other contributors that have really done the majority of this work. This really isn't my work, all these recent improvements. Okay, well, thank you.
All right, thanks, Alan.